Welcome back to the deep dive. Anyone who's worked with a large language model knows that magic phrase, right?
Hmm.
Let's think step by step.
Oh, absolutely. That simple prompt, it just unlocks everything. It activates what we call chain of thought or CoT.
And when you pair that with in-context learning,
Mhm.
where you give the model a few examples, it completely transforms how these AIs tackle hard problems. We're
Mm.
talking arithmetic, symbolic logic, things they used to fail at.
It's really the mechanism that pushes them from just pattern matching to something that feels a lot more like genuine multi-step reasoning. You're not just showing it the final
You're
answer.
showing it the work.
You're showing it the entire intellectual process. You're teaching it how to solve the problem.
Okay, let's unpack this, though, because as amazing as this CoT and in-context learning combination is, it has a really serious and I think often overlooked limitation.
Hmm.
I mean, think about the work involved. You have to create these perfect, handcrafted examples. You're literally writing out the ideal thought process for the model to follow. That is incredibly labor-intensive.
And that labor problem, it becomes a crisis when you push the model out of its comfort zone, when you give it a totally novel task, something it's never seen.
Like, say, some super domain-specific query.
Exactly. Or new abstract reasoning. All of its massive pre-training knowledge is suddenly, well, useless. It has to rely entirely on the few examples you give it right there in the prompt.
So going into the source material for this deep dive, we kind of assumed the conventional wisdom, which is more training on chain of thought must equal better reasoning. It feels intuitive, right?
Of course. If thinking is good, then seeing thinking steps for every single example should be the best possible way to train.
But, and this is the core finding that stopped us in our tracks, the researchers found that an excessive amount of CoT examples during the model's meta-training.
Which is the phase where it learns how to learn from context.
Right. Too much of that can actually cause its reasoning performance to seriously degrade later on when that detailed step-by-step guidance isn't available at inference time.
It's like the model becomes addicted to the detailed instructions, take them away, and it just flounders.
So our mission today is to unpack the CoT recipe. This is a formal solution these researchers came up with to modulate that precise mix of thinking and non-thinking examples. And you need to pay attention to this because getting this recipe right led to accuracy gains of up to 300%.
And not just in a lab. We're talking 130% on established, pre-trained LLMs. A 300% increase tells you we've been missing something fundamental about how these models actually learn to reason.
Absolutely. So let's start in section 1 and really define the specific challenge they were trying to solve with this CoT ICL approach.
So when we say ICL, in-context learning, we just mean giving the model a few examples of a task in the prompt, maybe 5, maybe 10. CoT just adds those intermediate steps, the thinking, to those examples.
And the problems with this are, well, they're both practical and structural. Practically, like you said, creating high-quality step-by-step demonstrations for every single scenario is just brutal. It's not scalable.
Not at all. And structurally, the sources point out that the real benefits of CoT often only show up at massive scale. We're talking the biggest, most expensive models. Smaller models tend to struggle unless you fine-tune them heavily.
But the biggest issue comes back to generalization, right? If the task is completely new, the model has to figure out the hidden rules, the underlying structure just from those few examples.
Precisely. And if those examples aren't perfect or diverse enough, the model just fails. It can't infer the structure.
Which means we need a way to test if the model is really learning the rules or if it's just, mimicking the text you gave it. We need a lab.
Exactly right. And to study this systematically, without all the messy variables of natural language or pre-training bias, the researchers developed what they call CoT ICL Lab 2.0.
Okay, let's spend a minute on this in section 2 because the lab setup is really fascinating. They didn't use English words. They used abstract tokens. Why was that so important?
Using abstract tokens, so just symbols, not words, let them define brand new synthetic functions from scratch. They built a system where the ground truth, the correct reasoning path, was always known. It has two main parts: a causal structure.
Which is basically the flowchart, right? The rules of the game that define how the tokens are supposed to interact.
Yep, you can think of it like a directed acyclic graph, a DAG, and the second part is a token processor, which is the logic unit that actually executes those rules.
So the goal of the training isn't language prediction. It's to see if the model can figure out that hidden function, those rules, just from the examples.
That is the entire game. That's the definition of reasoning generalization we're after.
And to track how the model was reasoning, they added a really clever innovation: special delimiter tokens.
Yes. Things like think start, think end, tan start, and tansend, These tokens act like structural fences in the prompt. They perfectly separate the input, the internal thinking steps, and the final answer.
Why is that separation so powerful for an experiment like this?
Because it lets them use what they call the forcing strategies. This is critical. Think of it like testing a student. You can ask them to solve a problem in their head, or you can demand they write down every single step.
I see. So the first one, the force think strategy.
That conditions the model to generate those intermediate thought tokens first. It forces the model to execute the full reasoning process. It's the show your work test.
And the opposite would be force answer.
Exactly. That tells the model, skip the thinking, just give me the final answer directly. This tests if it can solve the task just from pattern recognition without having to externalize the reasoning.
And the third one, no forcing, just lets the model do whatever it wants. This level of control is what let them find the hidden cost. So let's get to that in section 3, the big data collapse.
This is where the surprise really hits. We think these models are robust, but this showed they can become almost pathologically over-reliant on the style of data they saw during training.
Okay, let's start with the most extreme case, the over-reliance on chain of thought. The paper calls this the alpha dollar recipe. What did that training look like?
The alpha equals 0 recipe means the model's entire meta-training diet was only CoT examples. Every single sequence it ever saw showed the full step-by-step thinking. It learned that reasoning always looks like this.
And then they tested it. They took these alpha 0 models and put them in a co-poor environment. What happened?
Total catastrophic collapse. They measured this by changing a parameter in the prompt called dollars. And we should be really clear. Dollars is just the number of standard examples in the prompt.
Standard meaning question and answer with no thinking steps shown.
Right. So as you increase dollars, the model sees fewer and fewer of those perfect step-by-step guides in its immediate context.
And the data point they gave was just staggering.
It was. For their big custom model, TF12, when they used ForceThink, its accuracy went from a nearly perfect 0.93 when K prime was 0, so all CoT examples,
Down to...
all the way down to a dismal 0.18 when K prime was 39.
Wait, 0.18? That's not a performance drop, that's a complete failure. The model fundamentally knew how to do the task, but it couldn't execute because the scaffolding it expected was gone.
It's an addiction to the input format. It learned to expect the thinking process to be prompted by the examples. If it doesn't see those steps, it just breaks. It can't retrieve the right reasoning path.
And the other extreme, over-reliance on standard examples, the alpha interventory recipe, was just as bad.
Totally dysfunctional. Those models only ever saw question-answer pairs. So, predictably, if you asked them to force think to show their work, their accuracy was basically 0. They couldn't generalize the thinking process at all.
So the problem isn't just, can the model solve it? It's, can the model apply its reasoning capacity flexibly, no matter what the prompt looks like?
Precisely. And that brings us to section 4, the solution, the CoT recipe.
This CoT recipe is a formal, parameterized way to control that mix of kooky and non-CoTed examples during training. It sounds simple, just mix the data, but how you mix it is everything.
The key is the alpha parameter. This is part of a power law function that governs the shape of that mix across the whole training set.
Okay, break that down for us. What does a power law function mean here?
Well, think of it this way. If alpha is a small number, like 0, you're hitting the model with only CoT examples from the very beginning. But if alpha is large, say 2, you're easing it in. The training starts with mostly standard, non-thinking examples, and only later do you introduce more of the complex step-by-step CoT sequences.
So a high alpha is like slowly taking off the training wheels. You start with simple stuff and then gradually introduce the full annotated process.
That's the perfect intuition. And the breakthrough was finding that sweet spot. Alpha values like 0.5, 1, and especially 2, they successfully prevented that disastrous over-reliance.
And the champion here was the model trained with Alpha 2.
Oh, by far. The Alpha 2 model was incredibly robust. It could use the force-think strategy and keep a high accuracy around 0.78, even when tested with K prime at 39, where its prompt had almost no thinking examples in it.
Let's just restate that comparison, because the scale is incredible. The over-reliant Alpha 0 model dropped to 0.18 accuracy. The properly modulated Alpha 2 model got 0.78.
And that's where the huge performance jump comes from. That's an accuracy improvement of over 300% on their custom model. It's definitive proof that the model wasn't just copying a style. It learned the real underlying reasoning structure.
It's just an amazing return for something as simple as curating your data mix more intelligently.
Mm.
We focus so much on architecture and scale.
And here the key was just smart data prep. And we should also mention a side benefit they found. Diversifying the training data even more by randomizing things like input length and reasoning chain length help the model generalize even better to out-of-distribution tasks.
That makes sense. Variation forces a deeper learning of the rules. Okay, but the big question is, does this lab stuff actually translate to the real world, to the massive LLMs we all use? That brings us to section 5.
It does, and they verified it. They applied this CoT recipe to pre-trained LLMs, the Quinn 2.5 series, on a really tough, totally new symbolic reasoning task they called CIL Langsim.
Tell us a bit about that task. What makes it a good test?
It involves really complex logical manipulation of strings. We're talking precise string splicing, character offsets, abstract positional tracking. It's pure compositional logic, completely outside of normal language.
And this is the crucial part. The pre-trained Ken model scored 0 on this task before the meta-training.
Exactly, 0. That tells you that any performance gain comes purely from the CoT recipe, not from some general knowledge the model already had.
So what were the results?
The principle held up perfectly. For the Quen 2.57b model, using that robust Alpha 2 recipe gave them an accuracy boost of over 130% compared to the naive Alpha 0 model, especially in those CoT port test cases.
This is a lesson for anyone building or fine-tuning models. It's about balance and intention in your data. So let's give everyone some actionable guidance. If I'm building my data set, how do I pick the right alpha?
The guidance is beautifully practical. It all depends on what you expect at inference time. If you know you'll be in CoT-rich scenarios, where your prompts will always have plenty of detailed examples,
You think it could be more aggressive?
you can. Choose a low alpha, like 0 or zero point 0.5, and use the force think strategy. You'll maximize performance when you have that ideal scaffolding.
But what if my use case has sparse context? CoT poor scenarios. Maybe I can't afford the token cost for full examples in every prompt.
Then the risk of that performance collapse is very real. You need to choose a higher alpha, like 2 or even infinity, during your meta training. And crucially, you should probably pair that with the force answer strategy at inference to stop the model from trying and failing to generate thinking steps.
And for the holy grail, a versatile model that has to work well no matter what the prompt looks like.
For that all-arounder, you need to train with a mix. The researchers recommend training with alpha values in the range of 0.5 to 2. That gives you the best trade-offs across all the different scenarios and forcing strategies.
So this whole deep dive really boils down to one powerful insight. Teaching LLMs to reason isn't about overwhelming them with thinking steps. It's about carefully metering those steps with the CoT recipe.
That modulation prevents the model from developing this brittle dependency on how it was supervised. It ensures it learns the real task structure so it can reason effectively even when the context is sparse.
But there was one last finding in the research that really makes you stop and think about what's going on under the hood.
Yes. It connects to this whole idea of what AI thinking even means. Even for that powerful Quen 7b model, getting the chain of thought steps correct did not always guarantee getting the final answer correct.
Say that again. The model did all the thinking steps right, but still got the answer wrong.
Exactly. They found that in one test, for roughly 30% of the prompts that produced the wrong final answer, the model had actually predicted both intermediate reasoning steps correctly. So here's the final question we want to leave you with. What does this tell us about the relationship between thinking and knowing in artificial intelligence? Is that intermediate reasoning step truly a sign of understanding, or is it just another highly trained but ultimately separate and fallible sequence of tokens that can sometimes disconnect from the final output?